So I wish you all a happy new year. I hope you had a nice Christmas time and a nice New Year's party. So I hope you're ready to continue with our lecture on programming, data analysis, and deep learning in Python. Last year, what we did is we did linear regression using gradient descent. And I hope you noticed that it's not a very smart thing to do in the case of linear regression because basically it takes forever. It only finds approximate solutions. But gradient descent is a very simple and very general optimization method that we will, after linear regression, we will do logistic regression using gradient descent. And then we will do neural networks. And when we come to multi-layer neural networks, then gradient descent is actually not such a bad optimization technique because many of the more advanced optimization techniques don't work very well in this case. But let's just finish up with linear regression. I just want to show to you that there are much better ways to do linear regression than doing gradient descent. So if we look at the problem again that we looked at last year, we had a few data points. So basically, if we have on the x-axis we have 1, 2, and 3, and on the y-axis we have also 1, 2, and 3, and say we have 3 data points: one at 1, 1, one at 2, 3. And one at 3, 2. And now we want to fit a line in here. So let's say we want to fit a line like this. Does anybody remember which line we wanted to find? So what's the criterion for the line? How do we define which of all possible lines through the data points is the best one? Yeah, so what exactly do I optimize?
We minimize the distance from the line to all points, but the distance is squared.
Yeah, and you have to take care that you minimize this distance, right? You don't minimize this distance.
Yes.
So you minimize the vertical distance. So given that you know x, how much does your 2y deviate from your prediction y hat, right? So you look at these distances, and then you square them. So you get these 3 squares. And then you just sum the squares, and that's what you want to minimize. So these guys here, they would be your predictions, and these guys here, they are your data points. So basically, you say that your prediction, y hat, your prediction for y, if this is y and this is x, is wx plus b. So it's an affine function of x. Now, we did this by optimizing w and b through a gradient descent. And in the case of linear regression, that's actually very stupid because we could try to set up a system of equations and try to solve that system of equations directly. So if I just write this in reverse order, so it looks a bit nicer. If I write that b plus wx is y. And now each of these data points gives me one equation of this form. So b plus w, say let's take this point first. So x is 1 and y is 1. b plus w times 1 is 1. And then this data point, b plus w times, so x is 2. b plus w times x, x is 2, is y, and y for this data point is 3. And the last data point gives us an equation that b plus w times x, x is 3, is 2. Now we have this system of equations here. And we know that we cannot find a b and w to solve all three equations, right? Otherwise, we would be able to find a line that goes through all these 3 points. But such a line doesn't exist because these 3 points don't lie on a line. So does anybody have an idea of... Well, let's first rewrite the system of equations in matrix form. So we see that there's a 1 in front of here. Maybe I'll write it here. And now if we write that in matrix form, then we have 1 column of 1s. So the same system of equation. We have 1 column of 1s and 1 columns of 1, 2, and 3. 1, 2, and 3 times BW is 1, 3, 2. So this is actually, this is the same equation as this, right? So 1 times b plus 1 times w is 1, 1 times b times 2 plus 2 times w is 3, and 1 times b plus 3 times w is 2. Let's call this matrix A. And let's call this y. And now we know that we cannot find an x, we cannot find this vector x that solves this equation, right? What can we do instead? We cannot find an x that solves this, but what's the best thing that we can do? If you, yeah.
Here we can find x such that the distance between the two y hat is smaller.
Yeah, we can try to find the best x that approximates this. We can find an x hat that actually solves this equation. And we do this via the pseudo inverse. So we try to find x hat. Best x hat that solves actually so we find an x hat that solves A transpose A, x hat equals A transpose B. And this will actually be the best x hat, the best B and W that we can find. Okay. So this is A. So we first have to calculate A transpose A. A transpose A, which is, so we transpose A, 1, 1, 1, 1, 2, 3, times A, 1, 1, 1, 1, 2, 3, which is 1 plus 1 plus 1 is 3. 1 plus 2 plus 3 is 6. 1 plus 2 plus 3 is 6. And 1 plus 4 plus 9 is 14. Okay, so this is A transpose A. And then we have to calculate A transpose. Oh. Yeah, I should call this better. Let's call this B. There's already B here. Okay, that's why okay, sorry. Okay, then we calculate A transpose Y, which is 1, 1, 1, 1, 2, 3, times 1, 3, 2, is 1 plus 3 plus 2 is 6. And 1 plus 6 plus 6 is 13. So now we have this new system of equations. A transpose A is 3, 6, 6, 14. X hat is 6, 13. And now we can solve this using Gauss algorithm. So we write up the augmented matrix, 3, 6, 6, 6, 14, 13. Now we subtract the first row from the second row, we subtract 2 times the first row from the second row. So the first row is 3, 6, 6. This is 0, 2, 30 minus 12 is 1. So now we know that 2 times W, this here, this is a column for W. This was B and this was W. So 2 times W is 1. So W is a half. And now we can substitute this here. So 3 times B plus 6 times a half is 6. So we subtract 3 from here. So 3 times B is 3. So B is 1. I hope. So we know now that the slope should be a half. The slope for the optimum line is a half, and the offset is 1. And the nice thing here is basically we could do this we could find the best W and B in one step. So we didn't have to do like, I don't know, 2,000 iterations of gradient descent to find some approximate solutions. But we do one calculation. We just solve A transpose A, X hat equals A transpose Y. And we find the absolute best W and B. And it's not approximations, it's the best values for W and B. So what we can learn from this is that gradient descent is it's a nice optimization algorithm, very simple optimization algorithm in some cases, but in some cases we have much better techniques, right, to find to solve such problems. Okay, so let's code that in Python. So instead, remember that last time we wrote all this code up here. So we initialized our parameters, then we implemented this propagation function, then we implemented this optimization function, and then we had this modeling function. And we ran the entire thing for 10,000 steps with this learning rate, and it gave us some approximations for W and B. And now let's try to do the same thing in just one step. Basically, we just have to set up the matrix A. That's the most difficult thing, and then we have to solve this. So let's try to construct this matrix A. So first we need a column of ones which has the same shape as our x values. So these values along the x-axis, they go here, and then next to that, left to that, there should be a column of ones. So we had this, our column with the x values was here, train set x dot shape. Okay, so our x values has 406 rows and 1 column. And now we want to have a column vector of all ones that has the same shape. And we call that ones. Ones is np. Fortunately, there's a function in NumPy that's called ones, which gives us a column of all ones, or a matrix of all ones. And the shape of that should be the same shape as the train set x. So train set x dot shape. Okay, and now ones shape. So now both of these vectors have the same shape. And then we want to stack them horizontally. So the first column of our matrix should be all ones, and the second column should be all the x values. And we call this matrix A. A equals NP. Anybody remembers this horizontal stack function, hstack? Hstack. You just give it two vectors, and it stacks them horizontally. So we give it a list of what we want to stack. We want to stack the ones and the train set x values. And now the shape of of A is 406 rows for all our data points and 2 columns. And our y values, they are in train set y. Train set y dot shape. So also 406 rows, 1 column. Okay, and now we can do np.linearc.solve to solve a system of equations. And now we have to calculate this here. We just have to calculate A transpose A. This is matrix, and the right side should be A transpose Y. So we solve NP dot A transpose A, and the right side should be NP dot A transpose train set Y. Okay, and this should give us 2 values. I hope they are B and W. And now B is this and W is this. And I hope I didn't confuse B and W. So previously, our B was minus 40.63 and W was 10.05. But actually, the best B is minus 41.11 and the best W is 10.12. And here we can actually be sure that these are the absolutely best values for B and W, whereas with the gradient descent, they are always approximations of the best values, and we can never be sure that we reach the absolute optimum. Oh, and now you see that B is still a matrix with 1 value, so there is this convenient functions B dot squeeze. Oh, I think like this. Oh, so it basically it removes the brackets from the thing, and then I think we can put that into a float. Float B dot squeeze. Oops. Squeeze. Now we get the float. If you want to have the float out of that NumPy array. Okay. So this is much better because it's only 1 line of code. It's only 1 line of code. It's very fast, and it gives you the absolute best values, right? So it's much better than using gradient descent. But for people who are too lazy to type this and to set up the matrix A, there's a function in NumPy that's called polyfit. So if you are too lazy to set up A, use polyfit. And polyfit, you basically only give it the x and the y values. So WB is np.polyfit. Polyfit, I mean, fits a polynomial, right? Polyfit train set x. And let's look at the shape of train set x. Train set x dot shape. So unfortunately, polyfit doesn't want this column vector, but it wants a rank 1 array. So you have to remove the second dimension here if you want to use polyfit. And you can do this by calling reshape -1. So just squeeze it to 1 dimension. Train set y. And then the degree of the polynomial, which was 1. So now W is 10.12, which is exactly the same that we get with up here. And B is negative 41.115, which is exactly the value that we got previously. Okay. Now say we have values, our values look not like this, but they look more or less like this. If you have data which looks like this, it would be obviously a very stupid idea to fit a line to that, right? Can anybody guess on what kind of shape if you want to fit a polynomial? You can, yeah. Yeah, you can fit a parabola, right? You can fit a quadratic. So you can hope that you can fit a quadratic, a second degree polynomial to this data. And the nice thing is that you can use exactly the same method to do that, right? So you can use this method not only to fit lines. So if your vector here, B and W, if it has more components, that doesn't hurt this method, right? This method works equally well independent of how many components you have. So say you have y hat is how do we call these? Now B and W are not that nice anymore. Can we call them A0? Is that okay? Plus A1x plus A2x squared. So you have a model like this. And now you want to find A0, A1, and A2. Then basically, what you have to do is you set up the same system of equations like down there. So you say that A2, and then here you put x1 squared plus A1 times x1 plus, I should write it in reverse order again. So you have a nice shape. A1x plus A2x squared is y1. And say you have some data point here, which is, I don't know, maybe it's 1, 4. If you want to put the data point in here, or maybe you have 2, 4. So say this data point here is 2, 4, and you want to put it in the matrix. Then here you get a 1. For this, you get a 1. Then for this, you get the 2. And for this, you get 2 squared, which is 4. And then y will be 4. So you set a matrix like this. and 1 times A0 plus 2 times A1 plus 4 times A2 will be 4, and you do the same for all the other data points. And now this is your matrix A. Then this, well, previously we called X, and this we called Y. And then you do exactly the same. You do A transpose A, X hat as A transpose Y. And you solve this. And then you get your values for A0, A1, A2, and as many as you. I mean, you can generalize this to as high a degree of the polynomial as you want, right? So you can do the same for a 100-degree polynomial. It's just exactly the same. Okay, but if you want to get a 100-degree polynomial, it's even less work if you do a polyfit, because you can just do this. And then, of course, you need to put you get 100 parameters back. So let's call these A. You can do this, and then you get a 100-degree polynomial for, oh, you cannot see it. For your data. Okay, maybe we can execute that. So now our values A, they are these. Oh, okay, you get a lot of parameters. But you also get a warning. So Python gives you a rank warning. Polyfit may be poorly conditioned. Does anybody have an idea why you get this warning if you fit a 100-degree polynomial to your data points? Who thinks it's actually a good idea to fit a 100-degree polynomial to this data? Who thinks it's a bad idea? Why? Can anybody give a reason? Yes?
So if you have a higher degree of polynomial fit, then you have a really good fit in the short term. But for, let's say, longer data sets, it might really explode on one or the other.
Yeah. Yeah. Exactly. So in machine learning, this problem is generally called overfitting. So overfitting is a very general problem that you get with, it's a very big problem with neural networks, with deep learning. And I would like to explore this a bit in the case of a polynomial regression, because it's like trivial to see. And it's exactly the same problem that you will get when you use deep learning. Okay, so I brought you a different data set provided by MIT, by John Gutak. Import, so let's use pandas as PD. And now I hope I can load that. PD read CSV. So you read a comma-separated value file. I hope it's in data spring data CSV. Oh, yeah, it seems to be there as head. Okay, so this is the data. Let's plot it as dot plot. Oh, let's see what happens like this. Okay. Oh, no, this was not what I had in mind. So I wanted to plot x against, so x should be the mass. X should be the mass in kilograms, and y should be the distance in meters, and the style should be as this. Mass in kilograms, distance oh, there's some space here. Okay, so this is the data. And it's data from an experiment where they used a spring. They put masses of different, they put different masses at the end of the spring, and the spring got longer, and they measured how long the spring would get if you put different masses on that. Okay, so let's fit a polynomial to that. Maybe we can fit a line to that, np dot polyfit. So the x values are the masses in kilograms. The y values are in the same data frame, the distances in meters. And I want a first degree polynomial. And so I get two parameters, I call them A11 and A01. Okay, now let's look at the slope. The slope will be in A11. The slope will be 0.45, and the bias, so the y-axis bias will be in A01. So the bias, so it almost goes through 0 here. Okay, so let's calculate an estimation using this linear regression and add that to the data frame. So to our data frame S, we add a new column, we call it linear, which will be this bias plus the slope, A11, times the column with the masses. So our estimate, our linear estimate of the distance is the slope times the mass plus the bias, mass in kilograms. So now our data frame has this additional column here with the linear estimation. Let's plot that. My plot is s dot. Maybe I already plotted it somewhere here. Yeah. Let's copy that. And then in the same plot, let's do. Paste that again. The x-axis should be again the masses, but now the y values should be linear. And it should go into the same plot. And this I do by saying x equals my plot. So my plot here gives me back an axis object that I can use later to refer to the same plot. And I store that in this myplot variable. And then I can say axis equals myplot, and that tells Python to plot in the same plot. Okay. Yeah, okay, it's kind of okay. So our true data are these blue points, and our estimate, our linear regression, is this orange line. I think it's kind of okay here, but I mean, it's not as nice here. So maybe we can do a second degree polynomial. So let's just copy this line. Okay, so now we are now assuming that we don't understand the data, right? So say we have this data, we don't really understand what's going on. And if you're doing deep learning, what you would usually do is to start with a very simple network, see whether it fits the data well. And if it doesn't fit the data well, you would add more parameters. You would make the layers bigger, you would add more layers. That's what we're doing now. We're just adding another degree to the polynomial. Okay, so let's copy. Let's copy this line. So now we have a quadratic estimate. I think this was not what I wanted. So I wanted to say it's the 0th parameter of the second degree polynomial fit. Okay, so now my quadratic estimate is the bias term plus the linear term times the mass plus the quadratic term times the mass squared. I think that should be it. Oops. A02 is not defined. Oh, I should rewind this. Okay. So now in my data frame, I added this additional column with the quadratic fit. And let me try to plot that. So I copy this. And then in the same plot, I also want to plot the quadratic fit. Here I plot the quadratic fit in the same plot. Okay. Oh, that's much better. So our first model approximated the data, well, kind of okay, but the second degree polynomial gives me a much better fit to the data, right? So the green line is much closer to my data points. That sounds nice. Maybe I'll just add another degree to the polynomial and it will get even better. Let's call polyfit again. Okay. So let me do a third degree polynomial, which gives me another parameter, A33. So now I have the third degree polynomial. It's very simple with polyfit. I just increase this number back here, right? Then I add another column to my data frame. So it's a bias term plus the linear term times the mass plus the quadratic term times the mass squared plus the cubic term times the mass cubed. I think that looks okay. Let's plot that. In general, I think in general, this is not a stupid way to do this, right? So what sometimes people do in deep learning is they start with a super complex model with like very big layers, like a very deep network. And most of the time, this is, I mean, you can have a too complex network. So most of the time, it's better to start with a very simple model, see how well it works, and then increase the complexity of the model until you get a nice fit of your data. Oops. So I just want to plot the cubic term in the same plot. Cubic. Did I call this cubic? Oh, no, I called it quadratic. Oh, that was stupid. Okay, cubic. So I should rerun the quadratic, this, and I add this cubic column I plot these. Oh, okay. So now I see that the cubic model is even better, right? So my cubic model now is really close to the data. So we could conclude that actually the cubic model is the best of these models. Can anybody maybe repeat the problem that we might get with the cubic model? Yes?
If we now present the model any other data, it might have some wild guesses which are just completely untrue.
Yeah, if you use a model to predict the length of the spring when we put a mass of like 2 kilos, does anybody have an idea of what the cubic model would predict how long the spring would get if we hang 2 kilos on it? Maybe we can have a look. So say the mass of let's say we use this model, we use our cubic model, and we put 2 kilos on it. So the mass is 2 kilos. Does anybody have an idea what would be a sensible length for the spring if we put 2 kilos on the spring? Let's see what the model predicts. Oh, minus 3 meters. So our model now predicts that if we put more and more mass, so if we put up to 1 kilo on the spring, it would be like 40 centimeters long, but if we put 2 kilos on it, the length would get negative. So that's what we call overfitting. So one problem is that if we train our model on data within a certain range, and we have a very complex model with a lot of parameters, the model might start to do crazy things outside of that range, right? If we go outside of the range where we have data, our model might do crazy things. Maybe we can do that a bit even more interesting. Maybe we can fit now a 20-degree polynomial to our data. I mean, thinking that adding more parameters helps. Why not do for degree 20? So I call these params 20. So let's take our data, let's put a 20-degree polynomial, and I think we get some warning. So these are the parameters now for our model. Let's add a column to our data set. Degree 20. There's this nice function. If you have 20 parameters, then you don't want to write something like this, right? But if you have all the parameters in an array, you can use a nice function that's called polyval. Evaluates a polynomial, right? So you just give it the parameters, params 20, and the x values. The x value are in this column, mass in kilograms. Okay. Now we have this data. Okay. Now let me plot this for you. With the plot function. So let's plot all the models and let's plot the degree 20 model alongside. So degree 20. Okay. Now we see that actually the model of degree 20 is the best of all models, right? I mean, the 20th degree polynomial, which is this purple line, matches the points almost exactly. Does anybody have an idea what could be? Say I'm not interested in any masses above 1 kilo and below 100 grams. I'm only interested in masses in this range. So now I could say, well, the purple model is actually the best. It's the best of all models. If I want to predict the length of the spring, I use my purple model. Yes?
If I were to take another sample, maybe even the same spring,
Uh-huh.
it would probably not even work anymore.
Yeah. So now you have to take care that in this plot, we only evaluate the polynomial for these discrete steps here, right? So we never evaluated the polynomial between these points. Maybe we should do that and see what our model does between these points. Let's do some artificial masses with NP-A range, maybe, from 0.1 to 1.0 in steps of 0.001. Okay, these are my masses. And now let's evaluate the polynomial on these data points. But not on these, but on these. And length. Okay. And now if we plot plt.plot, did I import pyplot? I hope. Masses against length. Okay, so this is prediction of my model. So my model now predicts that at 100 grams, the length of the spring is about, I don't know, 10 centimeter. But at 50 grams, the length of the spring becomes negative. And at 900 grams, the length of the spring is 45 centimeters. But at 950 grams, the length of the spring suddenly becomes 11 meters. Right. You cannot, it's important to see that there's a risk of overfitting if you have data within a certain range. Say you have data points here, and then you train a model here, then you might get overfitting everywhere here in the regions where you didn't have data, but you can also get overfitting in between your data points, right? So your model might make crazy predictions like length of the spring of 11 meters in between your data points. Okay, so now a question for the natural scientists among you. If you look at the data, so now the procedure that we did is we took the data, we didn't even try to understand the data, and we just started to fit models to the data. Obviously, a much better method would be to look at the data and first to plot the data, explore the data, and to try to understand what's going on. Can maybe some of the physicists here, look at the spring data, and I think you don't have to be a physicist to see what's going on. So can anybody have a guess what's going on here with the data? Yes?
Do you wish to explain the behavior of the spring?
Yeah. So what's the physical process that created this data? So we had the spring, right? We put different masses on the spring, and this is our data. But why? What's a plausible explanation for the data? Yes.
Well, there is depending on material, etc., there are certain rigidities and certain maximum elongation of the spring. But in general, spring will behave in a way that it will elongate if you put a certain amount of weight on it, but it cannot elongate beyond a certain point here without actually taking irreversible damage. So that's probably why we find that plateau on the
Yeah.
right.
So here, up here, we have a very nice linear region where the spring of the length of the spring, according to Hooke's law, increases linearly with the mass that we put it. But here, at this point, we basically maxed out the spring, right? So here, the spring cannot get any longer. It reaches its maximum maximum length. So if we add more weight here, then the spring has already reached its maximum length, and it will not get any longer. So that's why we have this plateau over here. So based on this physical insight, can anybody propose a better model? Yes?
The logistic regression would kind of fit this nice. Logistic regression.
Logistic regression, yeah. So, okay, proposal 1, logistic regression. Can anybody think about some, if you think about whether you know some physical laws behind that, right? Can you use them to fit a better model? Oh, yeah.
What came to my mind was segment the data.
Yeah, okay, you segment the data. That's a very good idea. So you say that you actually don't want to use the same model for the entire data set, right? You segment the data. Where do you want to segment the data? At which point? I mean, how do you want to segment the data? Yeah?
In general, I would collect more spring data.
Okay, collect more data. That's always a good idea.
In that case, maybe like 250 grams to 700 grams. And I don't know if I want to take the range between 0 and 250 grams or not, but however, from 700 to a kilo, I would also have a new.
Yeah. So if you have overfitting, in general, the best way to fight overfitting is always to collect more data. That's always a good idea. But in this case, you can also segment the data here, right? And you say that your spring is behaving according to Hooke's law, to a linear model in this region, so you can fit this part with the linear regression. And up here, it's maxed out, so here you just fit a flat line to that. You say that here you say that the maximum length of the spring is only 45 centimeters, so here you fit a flat line, and then maybe at some mass the spring will break, and so you might also want to find that point. Okay, so here it's a very good idea to actually split, to get some insight into your data, get some insight in the process that created your data, and based on that insight, to segment your data and to fit different models to different parts of the data. So only fit a linear part to this left part, a linear model to this left part, and then a flat line to this part. Okay, so that's basically all I wanted to say for linear regression and overfitting for now. Are there any questions for linear regression and overfitting? Okay, so if we, well, basically I have to clean some blackboards. So now we are still in the region of supervised learning, supervised machine learning, where we have data that we want to learn. And we just looked at regression, where we want to learn a function that maps to a continuous variable. And now the next step would be to look at classification, where we want to predict a categorical variable. So basically, we want to look at different flowers, and we want to recognize which kind of flower it is. Or we want to look at images, and we want to recognize whether it's a cat or it's not a cat. Or maybe we want to look at images and we want to see whether there's a dog in the picture, or a ship, or a cat, or whatever. And the first thing that we will look at is binary classification, So if we have some data about flowers, say the length of the leaves of the flower, can we say whether this flower is a certain kind of flower or not? And the method that we are looking at is logistic regression, because later neural networks are basically nothing than a series of logistic regression units. Okay, so we're looking at classification. In particular, we're looking at binary classification. And we're using logistic regression to do that. Okay, so say we have a number of training examples. Xi, yi, where x is a vector. So x is element of, it's an n-dimensional vector, and y can be either 0 or 1. So y can be nothing else but 0 or 1. So n here, it's the number of features in our feature vector x. Then we have I as the number of our training example, and we have m examples, or m training examples. So we have a training set, which is just the set of these vectors, x, y, yi. And what we will do is we will put all our x, so all these x's, xi is it's basically it's a column vector, right? With n entries, and now in order to make our implementation easier later, what we want to do is we want to put all the x's, we want to put them into a matrix. So we will construct a big matrix X, and basically we will just put all the training all the x's. We will just stack them next to each other. So this will be x1, x2, x3, x4, and so on until xm. We have m training examples. Okay. So that's what we do with our x's. And then our y's, we will just put them into a row vector. So we will have, so these are the x's. And the y's from our training data, we will put them into a vector like this. So it will be just a row vector with y1 here until ym here. Okay. And now our task, similar to linear regression, will be to predict y from x. So I give you x, and I want you to give me to predict y for that. So given x, so the task is the following. Given x, predict y hat, or calculate y hat as a prediction for y. And we will have a number of parameters for that. So the idea is the following. If we would like to do that with linear regression, so we could try to do that with linear regression. So that's our first idea. Our first idea is to use linear regression because that's what we know. So here we say that y hat is, so basically I multiply each of the each of the elements of x with a certain number. So say I have certain weights. So if my x is the following, so x1, so xi is the following vector, xi1 to xi n. Now what linear regression would do is to multiply some number with the first element and add to that some number times the second element and so on, right? Maybe I can write that here. So I would do w1 times x1 plus da 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 plus wn times xn. So I add up all these guys and then I add b to that. And now this I will write as a scalar product. So I will write w1 to wn times x1 to xn plus b. So this is exactly the same. So this is w1 times x1 plus w2 times x2 plus wn times xn, right? And I will write this simply as w transpose x plus b. So I take this vector w, so this is w, this is x, so this is w transpose because it's a row vector. Okay. Yes?
Can you say again what the plus signs mean?
These plus signs? Oh, it's just to say that you add up all these, so this basically removes this bracket. So this is not a vector. So you take the first component of x, you multiply it with the first weight, and you add that to all the other components of x times their respective weight. So each of the components of x gets a weight, w, and then you add up all of these, and then you add this bias term here, b. Okay. Any more questions? Okay. So, what's the problem with this? Can anybody see what's the problem with doing that here?
This might not yield any integer between, any flow between 0 and 1.
Yeah. So basically, with this, you get any real number, right? You can get anything from minus infinity to infinity. So basically, you get the whole range. Depending on the weights and the bias, you get the whole range. Does anybody have an idea of how we can restrict this to force it between 0 and 1? So I want to take this and I want to force it to be, I want to apply a function to this that forces this to be between 0 and 1. So it's basically our second idea. idea 2. I use a function to force it between 0 and 1. That's a logistic function. And the idea is to use a function of the following shape. So this part gives me any real number, right? And now I want to, if this is 0 and this is 1, I want to map this to the range between 0 and 1. And I will take some S-shaped function. Right? So if this gives me any point on this line, and then I apply this function to that, then later, after that, I'm in the range between 0 and 1. So now my only task is to find some function which has this nice S shape and gives me values between 0 and 1. And the function that's commonly used is the sigmoid function, which is this. There's nothing magical about this function. It's just a function that is differentiable everywhere and maps me this entire x range to the range just from 0 to 1. And the function is this. Sigmoid of z is 1 divided by 1 plus e to the minus z. Right? So if we go towards infinity here, then z becomes infinity. Then we have negative infinity here. And e to the negative infinity is 0. So the entire thing becomes 1. And if we go towards infinity, if we go towards negative infinity here, if we go towards negative infinity here, then negative infinity becomes infinity. E to the infinity is infinity. The entire thing becomes 1 divided by infinity. So it approaches 0. So as we go in this direction, we go towards 0, and as we go in this direction, we go towards 1. Let me just plot this function maybe for you, so you get a feeling for the function. Let's open a new notebook. Oops. File, new notebook. Logistic regression. Import think here. No. Okay. Import numpy as np. Import matplotlib.pyplot as plt. Then let me just get some x values between negative 5 and 5. X is np.linspace between negative 5 and 5 in 100 steps. I define this function, def sigmoid of z, return 1 divided by 1 plus np.exp z. Can anybody say what's nice about using np.exp here? Why did I use np.exp at this position and not math exp? Yeah.
Probably because we can deal with vectors.
Yeah, because now the parameter z can be any vector, right? And the function, I can apply the function to an entire vector, and it will exponentiate every element of the entire vector. Okay. Now I say that S is sigmoid of x, and I plot this plt plot x against S. Oops. I think e to the minus z. So this is the function that I wanted, right? So it's a nice, smooth function between 0 and 1, and it maps all the real numbers to that range. Okay, and now the idea is not to use this as a linear regression, but to apply the sigmoid function to this. So afterwards, I will get a number between 0 and 1. So the idea is the following, that I use as an estimator y hat is sigmoid of W transpose X plus B. Okay, and now the general idea is the following. Now I just need to find W and B. I just need to find the best W and B. And I want to do that using gradient descent. Does anybody remember what I will need for? What do I need to be able to use gradient descent to find W and B here? Yes? I need a loss function. Okay. So if I calculate this, given I have some W and some B, and given I have some X, I can calculate y hat. And I will have some 2y for my training example. And I need some loss function that for one training example tells me how good my estimate is, right? So I need a loss function first. So I need a loss function. I will call that loss of y and y hat for single example. So it's the deviation between y hat and y for single example. Does anybody remember the loss function that we use in linear regression? Linear regression. The loss of y and y hat was, yes? Just the squared residual, because the cost function reads then sum over all the examples. So this is just a single example. So the loss is y hat minus y squared. So now we could go ahead and use the same loss function, but actually that's a very stupid idea. And the reason is that that's a very stupid idea is that in the case of this loss function is perfect for linear regression, but in the case of logistic regression, this loss function later gives me a non-convex optimization space. So at least the cost function then would have many local optima. And when I use gradient descent, I would get stuck in local optima here. So for that reason, in the case of predicting categories, I use a loss function that's called a cross entropy loss. So logistic regression. I use cross entropy loss. And the loss function is the following between y and y hat is negative y log y hat plus 1 minus y log 1 minus y hat. I admit this looks a bit strange. So it basically makes sense if you think about the fact that y can only be 0 or 1, right? Y can never be anything but 0 or 1. So in the case that y is 1, then, so if y is 1, then the loss of y, which is 1, and y hat, is, okay, y is 1, so I have this minus sign, negative log y hat. And y is 1, so 1 minus y is 0, so this entire part disappears, right? So if y is 1, then the loss is just minus log y hat. And if y is 0, then this part disappears. 1 minus 0 is 1, and the cost is just this. So if y is 0, then the loss is 0 and y hat, which is minus this part, log 1 minus y hat. Okay. And now we can plot these two functions and see how they look like. I think I have this here. So if we plot these two functions, x is NP lin space, so I will test values between 0 and 1 with 100 steps, maybe. And let's first, if y is 1, so it's a loss if y is 1, maybe I can write it like this, is gleich minus np dot log x. Oh, divide by 0, okay. And now if I do plt plot x against ly1. So if y is 1, the loss looks like this, which basically tells us if the true value is y and our current estimate is 0, then the loss is very, very high, right? If y is 1 and the our current estimate is also 1, then the loss is 0. And in between here, we just say that having very wrong estimates is very, very bad. And having good estimates, it's good. Maybe we can also look at it in the case that y is 0. So if y is 0 is negative np log 1 minus y hat. Plt plot x against ly0. Okay, if the true value is 0, then the loss is like this. If the true value is 0 and our current estimate is 1, then the loss is very, very high. If the true value is 0 and our current estimate is 0, then the loss is 0. And we penalize wrong estimates very hard. Okay. This is just to argue that this loss function actually makes sense. It also makes sense from a probabilistic perspective. It basically measures the cost entropy between random variables. But I think for us it's okay that it's a loss function that makes sense. And it does what we wanted to do. And what's also nice, it's very nice to differentiate, and later it makes a lot of terms disappear if we differentiate. Okay, So now we have the loss function. What's missing? What's the next step? After we have the loss function, what's the next thing that we need? Yes? The cost function, yes. Next, we need the cost function. Loss function just measures the loss for a single training example. And now we need to define the cost for our entire training set. Cost function J of W and B for entire training set. Okay. Given that we have this loss, can anybody propose a cost function? J. So J, W, B. Okay, we have the loss for every training example. Can anybody propose some cost function for the entire training set? What's a simple thing that we can do? We know the loss for every single example. What's a simple thing that we can do? Yes. Yeah, just sum up all the losses for all the training examples. So we just sum I equals 1 to m the losses of the training examples. And now there's one thing that we do here is because now the cost increases if we have more training data. So we just divide by the number of training examples. So we don't take the sum of the losses of the training examples, but we take the average loss per training example. Oh, that's just our cost function. It's very simple, right? So we have a loss for every single training example, and our cost for our parameters W and B is just the average loss. Okay, maybe we should write that up. So this is 1 divided by m of the sum over all training examples of the losses, and the loss was this. Negative yi log y hat I plus 1 minus yi log 1 minus y hat I. Okay, that's it. Okay. Now, what we want to do next is we want to do gradient descent. So we want to find, let's first find the optimal vector W. So how do we find the optimal vector W given that this is our cost? We want to minimize the cost. We want to find the W that minimizes this cost. What do we have to do? Yes?
We apply the derivative.
Yeah, we have to find the derivative with respect to W of this. And then if we have the derivative, then we can do our gradient descent, and we can always walk into the direction of decreasing costs. Okay, so basically, we find the partial derivative of the cost function with respect to W. The derivative with respect to W of our cost is, okay, so this is just the derivative with respect to W of this thing over there. 1 divided by m, sum over I equals 1 to m of the losses. Y hat, I, and y, I. Okay. And now I can use that the derivative is linear. It's a linear operator, right? So I can just pull this factor and the sum, I can pull them out of the derivative. So this is 1 divided by m times the sum of I equals 1 to m of the derivative with respect to w of the losses. Okay, and now I just have to find the derivative of the loss function with respect to w. So this is because the derivative is linear. Okay, let me just do the first two steps. Now I have to find the derivative of this loss function here, of the cross entropy loss, with respect to w. So the derivative with respect to w of the loss of I should say y and y hat, then it becomes a bit nicer. Y and y hat. Sorry. Now let me just plug in what y hat is. So this is a derivative with respect to w of the loss of the true y. This is just my training data, right? This is just a number that I can look up. And what is y hat? Can anybody say what y hat is? Yes?
It's just a sigmoid with the
Yeah, it's just this thing up here, right? So it's my estimate for y. It's the sigmoid of w transpose x plus b. Sigmoid of w transpose x plus b. Okay. There should be a small I here. This looks a bit daunting, but we can use the chain rule now. So our loss function, it's now a cascade of functions, right? It's a function of a function of a function, right? And if I have a cascade of functions, I can use the chain rule. I hope you remember the chain rule. So the chain rule is the following. The chain rule is it's a tool to differentiate a cascade of functions. So if I have a function f of g of x, a function of a function, and I want to differentiate that, then this is, so f of g of x prime is f prime evaluated at the point g of x times g prime of x. I hope you remember this from calculus. And I can also write this a different way, which will be more convenient here, that the derivative with respect to x of f of g of x is the derivative with respect to g of x of f of x times the derivative with respect to x of g of x. So this is just a different notation for the same thing, right? Okay. So what we have to do now is we just have to apply the chain rule to this cascade of functions, and we have to apply it a number of times. And if we later go towards deep learning, Deep neural networks are nothing but a very deep cascade of functions. It's a very deep cascade of functions. And there will be many, many parameters, W, that we want to optimize. So we will want to calculate the derivative to lots of parameters W within a very deep cascade of functions. So deep learning is basically nothing but applying the chain rule over and over and over again. And there's an algorithm in deep learning that's called a backpropagation, where the only point of that algorithm is an efficient way to apply the chain rule if you want to differentiate with respect to a lot of different variables. So it basically, the backpropagation algorithm later avoids you from calculating the same things over and over again if you want to differentiate with respect to many different variables. And it stores all the intermediate results so that you can very efficiently differentiate with respect to many variables. But basically, from now on, towards deep learning, it's just a chain rule. Right? Chain rule is the most important tool here. Okay, so I think we're done for today, and I'm happy to see you next week. Thank you.